Today we're going to start with something very trivial, and then we're going to make it harder and harder as we go on. So we're going to start with the pigeonhole principle. It's a very simple principle. Let's say I have a set of pigeons and a set of holes, and I'm putting the pigeons into the holes. If the number of pigeons is more than k times the number of holes, then there is a hole that has at least k plus 1 pigeons in it. Right? Very trivial. So basically, let's say I have my pigeons here. And let's say I have 1, 2, let's say n pigeons. And then I have my holes here. And the number of holes is much less. So I have m holes. And I have a function f that is mapping every pigeon to a hole. Okay. Now, I don't know much about this function. All I know is that every pigeon is mapped to some hole, right? But the number of pigeons, n, is more than k times the number of holes. So n is more than k times m, and here k is a natural number. So I claim that there should be a hole that has at least k plus 1 pigeons mapped to it. And this map is what we call f here. Okay. Now, why is this the case? Let's prove it. It's actually very easy to prove. So let's say this is not the case. Let's just try to do proof by contradiction. So suppose that every hole has at most k pigeons in it. So suppose that for every hole, if I look at the pigeons that are mapped to this hole, their number is at most k. Okay. So how many pigeons can I have in total? I can just count the number of pigeons in hole 1, and then add the number of pigeons in hole 2, number of pigeons in hole 3, and so on. So the total number of pigeons, n, should be the sum of the number of pigeons in each of the holes. So sum of f inverse of h, where h is in h, okay? But we are assuming that each one of these is at most k. So I would say this is the sum of h in h, k, actually less than or equal, right? But then I have m elements here. So what I just proved is that n is less than or equal to m times k. But my assumption was that n is bigger than m times k. So this is a contradiction. And so this contradiction shows that there should be a hole that has k plus 1 pigeons. Again, it's a very trivial thing. But now we're going to solve a bunch of problems using this trivial idea of the pigeonhole principle. And we're going to see that it actually gets quite complicated. And the reason it gets complicated is because usually in the problems, you don't know what your pigeons and your holes are going to be. So you see a problem, you don't even know that this is a pigeonhole problem. You have to somehow define these two sets. You have to somehow figure out what you're going to consider as pigeons and what you're going to consider as holes. And it can get very creative. So let's start with a simple problem. Let's say that we have a 3 by 3 square, and we have chosen 10 points in this 3 by 3 square. Now, I don't know anything about how these points are chosen. It can be any combination of points. Okay. I want you to prove that no matter how the points are chosen, there are 2 of them that have a distance of at most square root 2 from each other. Okay. So again, here, the main problem is what is my set of pigeons? What is my set of holes? Now, here's what I would do in this case. I would just say, let's turn this into a grid. Let's just draw these lines. And I'm not great at drawing, but just imagine that these are all 1 by 1 squares. Okay. So I have 9 squares, 9 unit squares here, and I have 10 points. So let's say that my set of pigeons is basically my 10 points. And let's say that my holes are the unit squares that I just created here. And of course, I have 9 unit squares. So this means that two of the points have to be in the same square. It doesn't mean that exactly two of them have to be in the same square. You see that, for example, these two are in the same square, but these two are also in the same square. But I know that there exist 2 points that are in the same square. And that's all I'm going to use. So if I have 2 points in the same square, their distance can be at most the length of the diagonal, which is square root of 2, because this is like these small squares are 1 by 1. So the diagonal has a length of square root 2. Okay. So whenever I have 2 points in the same square, their distance is going to be at most square root 2. And because I've proven that I definitely have 2 points in the same square, I have proven that I have 2 points that have a distance of at most square root 2. Okay. Now, I explained this one in a lot of detail. I will not use this much detail for the next problems. Okay, look at this problem. We have a number of people, let's say n people, and they attend a party. And let's say that in this party, some of them shake hands. And let DI be the number of people who have shaken hands with person I, or, well, it's a mutual thing. So the number of people that person I has shaken hands with. We want to prove 2 things. And actually, the second one is where I'm going to use Pigeonhole, but the first one is something we need in the future sessions. So the first thing I want to prove is that if I take the sum of all the DIs, that sum is even. So I go around, I ask everyone, how many times have you shaken hands? I sum up these numbers, the sum has to be even. Why is that? Well, this is actually pretty easy to see. Let's say I have 2 people, I and J. And let's say that they shake hands. This one handshake is counted in DI and DJ. So every handshake is adding 2 to this sum. So this sum has to be even. Okay. So again, this part is just something that we will need later on in this course. But the second part is the more interesting part. Prove that there are 2 people that have shaken hands with the same number of people. So prove that there are 2 people, I and J, where DI is equal to DJ. So when you have problems like this, it makes sense to try some simple examples. So let's say I try an example with 4 people. So let's say these are my 4 people. And let's say I connect 2 people if they have shaken hands. So let's say I say this one has shaken hands with this one, and like this. And then I just count how many times each person has shaken hands. So this one has done once, 3 times, 2 times, and 2 times. So as you see, I have 2 people who have the number 2. I have 2 people who have each shaken hands with 2 other people. Okay, why does this always happen? So let's look at this. Let's see what values can this DI take. So DIs, again, remember DI is the number of people who have shaken hands with person I. So what is the range of DI? What is the smallest value that DI can have? 0. What is the largest value that DI can have? N minus 1. Yeah, well, we're assuming people are not crazy and are not shaking hands with themselves. So yeah, so the value of DI is between 0 and N minus 1. So maybe I can use the values of the DIs as my holes, and I can use the people as my pigeons. But the problem is that now I have the same number of pigeons and holes. Right? So I have N different possible values for DIs, and I have N different people. So maybe I have 1 person with every possible value of DI. But is that possible? Can I have 1 person who has not shaken hands with anyone, 1 person who has shaken hands with exactly 1 other person, 1 person who has shaken hands with 2 people, and so on, and 1 person who has shaken hands with everyone else? No. Because if I have someone who has shaken hands with 0 other people, then I cannot have another person who has shaken hands with everyone else, with n-1 other people, because these two persons have either shook hands or not, right? So that's not possible. So this gives us a way of doing the casework. So I say, let's do this. Let's look at all the people and let's see if we have someone whose D value is 0. So I say case 1 is that there is someone, some I, such that DI is 0. Okay. If I have someone who hasn't shaken hands with anyone else, then what does this tell me? This tells me that for every person that I have, for every J, the value of DJ is going to be between 0 and n-2. Because I have one person who hasn't shaken any hands, so I have this person I, and so any other person J that I have can at most shake hands with everyone else other than I, but there are n-2 people here, right? So the value of DJ is between 0 and n-2. Now I can use the pigeonhole principle. I can say I have n-1 different possible values for these, but I have n people. So 2 of them have to have the same value. Okay. So in this case, I say 2 people have the same D value. Okay. This was case 1, the case where there was someone who didn't shake hands with anyone else. But I can consider the other case, which is that there is no one, and this is like negation of exists. There is no one such that DI is 0. But this is great. This means that I cannot have the value of 0 among my D values. So my D values are going to be between 1 and n-1, right? So I have n-1 different D values, but I have n people. So again, there are 2 people who have the same D. So in this case, we could use the pigeonhole principle, but we had to be a little bit careful. We had to do a small casework. Okay. Let's go to the next one. I want you to prove that there are 2 natural numbers x and y, such that if I look at 9 to the power of x and I subtract 9 to the power of y, the result is a multiple of 2024. So another way of looking at this is that I look at the powers of 9 and I look at the remainder when divided by 2024. And what I'm saying is that there are 2 different powers of 9 that definitely have the same remainder when divided by 2024. Okay. Why is this pigeonhole? Again, you have to somehow tell me what are the pigeons and what are the holes. So let's do this. Let's consider a function f that takes a power of 9. So let's say it takes 9 to the power of x, and it maps it to its remainder modulo 2024. And I'm going to use C++ notation. Okay. So I want to basically say that the powers of 9 are my pigeons, and the remainders modulo 2024 are my holes. But the problem is that now my set of pigeons is infinite. Right? Is that really a problem? I would have a problem if my set of holes were to be infinite, right? But all I need here is that I want my number of pigeons to be more than k times the number of holes. So if I have infinitely many pigeons, I just take k times the number of holes plus 1, and I just ignore the other pigeons, right? And I can still apply the same theorem. So if my number of pigeons is infinite, I'm fine with that. So basically here, when I'm saying P and H are finite sets, I only really need finiteness of H. P can be infinite. And this is exactly what's happening here. So I have the different powers of 9, and I take them as my pigeons. So my set P is like 9 to the power of 0, because remember 0 was in it. 9 to the power of 1, 9 to the power of 2, and so on. It's an infinite set. Okay. Now, what are my holes? My holes are the different remainders that I can have modulo 2024. So if I divide the number by 2024, what are the different remainders that I can get? I can get 0, 1, 2 to 2023. Okay. So here's the thing. The number of pigeons is more than the number of holes. So there should be 2 pigeons that go into the same hole. Okay. So this means that there should exist 2 elements. Let's call them 9 to the power of x and 9 to the power of y. And these 2 have the same remainder when divided by 2024. So if I just subtract one from the other, then this has to be a multiple of 2020. Okay. So basically 9 to the power of x has the same remainder as 9 to the power of y modulo 2024. And therefore, 9 to the power of x minus 9 to the power of y is a multiple of 2024. Of course, I have to be careful. I don't have to know. I want to choose x to be the bigger one, but I don't have to. Even if this right-hand side is negative, it makes sense. Okay. But now, the thing here is I don't really need all the powers of 9. I could just take the first 2025 powers, right? So I know that I will find my solution in the first 2025 powers. Or I could take any 2025 members of this set, and among them there would be 2 that are mapped to the same remainder, and then I would find the solution. Okay. So in some sense, we proved more than we needed. We proved that there are infinitely many solutions to this, right? Because this is an infinite set. Just take the first 2025 members, you find the solution. Take the next 2025 members, you find another solution, and so on. So there are infinitely many solutions to this. Okay. Great. Let's look at this next one. So I draw a 3x3 grid. Actually, can I draw a grid here? No. Okay. Let's say I can try to do this and okay. So let's say I draw a 3x3 grid, and in each of these cells, I want to write either 0 or 1 or -1, right? But I want to do it so that if I look at the sum of the numbers in all the rows and the sum of the numbers in all the columns and the sum of the numbers of the diagonals, I want these sums to all be different. Okay. So this is like kind of a Sudoku, like the opposite of Sudoku. So for example, let's say if I write 0, 1, -1, 1 here, -1 here, 0 here, 0 here, -1 here, and 1 here. This is not a solution, right? Because the sum here would be 0. The sum here is also 0. So I already have 2 sums that are the same. I want all of these sums to be different. I actually did a terrible job here because this is also 0. This is also 0. This is 2. This is -2. This is 0. And this is 1. Okay. So I want to make sure that all of these numbers are different. The question is this possible? Okay. So this is an example of how I would give you problems in the exam. I will never tell you the answer. You have to guess the answer and then prove it. So I don't tell you if it's possible or not. But in this case, it's not possible. Now, why is this not possible?
7 minus 45, but there's a.
Yes. So if we look at the different sums that we can get, each of these are the sums of 3 sets. So the values are going to be between -3 and 3. And there are 7 different values there. But I have 8 sums. So 2 of these sums have to be the same. So no matter how I fill out this table, I'm going to get the same sum for 2 of these. So it's impossible. Let's go to the next problem. We're going quite fast, actually. We might finish the problems before the time. That's good. Okay. So here's the next problem. Let's say that I have a set X of integers, and let's say that there are n integers in this set. Now, I want to take a subset of my set such that the sum of the numbers in this subset is a multiple of n. Okay. Now, one trivial way to do that is to take the empty subset, because the empty subset has sum 0, and then 0 is a multiple of every number. But I intentionally say that you cannot take the empty sets. Okay. So prove that you can always take a subset such that the sum of the numbers in this subset is a multiple of n. So let's do an example again. Let's say my n is 4, and I just take 4 numbers, 2, 7, 5, and let's say 10. Okay. I claim that there is a non-empty subset here such that the sum of the elements is a multiple of 4. Well, you can just take 10 and 2, right? And then the sum is 12, which is a multiple of 4. Now, what I want you to prove is that this is always the case. So no matter what my n is, and no matter what my set X of n integers is, I can always find a non-empty set whose sum of elements is a multiple of 4. And then as a hint, I would tell you to think about this problem. We were thinking about remainders. So here we want to do something similar. Okay, let's see what we can get. Let's just do some attempt at this. So let's say this is our first attempt. Let's say my wholes are the different remainders modulo n. Okay, so my wholes are just going to be 0, 1 to n minus 1. And let's say that my pigeons are all the subsets of my sets, subsets of X. And my function f that maps pigeons to wholes takes a subset y and maps it to the sum of all the elements in y modulo n. Okay, so I'm going to say take any subset and just compute the sum of the elements in there and see what is the remainder when you divide by n, and you map it to that. Okay. So how many subsets do I have? The size of P is 2 to the power of n, right? But minus 1 because I don't want to consider the empty sets. So let's say this is non-empty subsets of X. Okay. What is the size of H? N, right? So I'm mapping 2 to the power of n minus 1 pigeons to n wholes. Well, the number of pigeons is more than the number of holes, so I can say that there are two pigeons that are mapped to the same hole. But does that give me an answer? It just tells me that there are two subsets that have the same sum modulo n. But that doesn't mean that I can create a subset that has some 0 modulo n. Right. So let's do an example here. Let's look at some of the subsets here and see what they're mapped to. So for example, if I take the subset 2, 5, 10, okay, what is the sum here? 17. What is 17 modulo 4? So if I take the remainder of 17 modulo 4, it's 1. Okay, if I look at 5 itself, this is also 1. The remainder is 1. So I have two sets that have the same remainder, and this is all I've got here because I'm saying the number of pigeons is more than the number of holes. But can I somehow combine these two sets to get another subset where the sum of the elements is a multiple of n? So the sum of elements is 0 modulo n. Well, in this case, I can. Because in this case, I got lucky, and this second one is a subset of the first one. Right, so I can just look at the first one minus the second one. So I just remove the elements of the second one from the first one, and I'll get 2 and 10, which has to be mapped to 0. Right? But I could do this only because I got lucky, only because my second subset was already a subset of my first subset. Okay? I can't do this in general. If in general I have two different subsets, let's say y1 and y2, and let's say they are mapped to the same number. So if I take their sum modulo n, it's the same. I can't just say, look at the elements that are in y1 but not in y2. Right? Because there are also elements that are in y2 but not in y1, and then the sums just don't work. So this tells us something. If you look here at the number of pigeons that I have far too many pigeons. Right? I mean, I just need to have more than n, but I have like 2 to the power of n minus 1 pigeons here. Right? But then on the other hand, I know that if I find two answers here, if I find two subsets y1 and y2 that are mapped to the same number, if one of them is a subset of the other one, I can solve the problem. So maybe I shouldn't take all of these pigeons. Maybe I should just choose some of the pigeons. And I want to choose subsets such that any two chosen subsets have, again, this property that one of them is a subset of the other. Okay, so this is going to be my second attempt at this problem. So let's do attempt 2. Okay. I want to choose a bunch of subsets, and I want to say that each one of them has to be a subset of the other one, and so on. So one easy way of doing this is that I take the empty set, and then, okay, let's say my original set was like x1, x2 to xn. Okay. The subsets I can take are these. I can take the empty set, and then I can take x1, and then I can take x1, x2. Basically, I'm taking all the prefixes here, x1, x2, x3, and so on, until I take everything. Okay. So generally, I'm going to look at subsets of this form, xi, which is going to be all the xj's where j is less than or equal to I. So xi is the first I elements of x. Okay. And this is by some order. I don't care what the order is. I just ordered the elements of x in some order. And then I say xi is the first I elements of x. Okay. Great. Now I say that my pigeons are these xi's. So how many pigeons do I have? Well, right now it's n plus 1. but I also had this extra requirement that I can never take the empty set, right? So maybe let's have it for now because it helps, but you can also do a casework, you can remove the empty set. But how many pigeons do I have right now? I have n plus 1, right? Okay, which is great. So I have n plus 1 pigeons, and I'm going to use the same function as before that maps every subset to the sum of the values in that subset modulo n. Okay. So now I have n holes. So this means that 2 of these subsets have the same sum if you only consider the remainder modulo n. Okay. So I have 2 subsets. There are 2 subsets. Let's call them xi and xj. And let's just assume that j is bigger than I because there are 2, I can order them in whatever order I want. Such that the sum of the elements in xi is equal to the sum of the elements in xj mod n. So these 2 sums are not necessarily equal, but if I look at their remainders when divided by n, they have the same remainder. Okay, but this is great. Because if I look at xj, it has all the first j elements. So it has like x1, x2, again, a small x are elements, big X are subsets. x3, so on, xi, xi plus 1, so on to xj. So these are all the elements that are in the set big xj. Okay. And these ones are the elements that are in the set big xi. Right? So I can just subtract them. I can just take these elements. And if I just take these elements, then their sum has to be a multiple of n, because the sum of these first I elements had the same remainder as the sum of all the j elements. So this part has to be a multiple of n. So I found a subset whose sum is a multiple of n. Right? And this is a non-empty subset too, because I and j are different, so I have at least one element here. Now I could do this because I added the empty set in my pigeons. If I didn't have the empty set, this would not work. Right? Because I have n plus 1 pigeons here. So if I didn't include the empty set, I would have only n pigeons, and then I couldn't really apply the pigeonhole principle. Okay. But let's see what would happen if I did the same thing, but I didn't consider the empty set. So I would have n pigeons here instead of n plus 1. But I can do something similar to the problem with shaking hands. I could just say, okay, I have these n subsets without the empty set, and all of them are non-empty. So I just look at the values that I get when I sum the elements in every subset and I take the remainder modulo n. If one of them has a sum that is a multiple of n, then I'm done. I already have a solution. One of these had a sum that was a multiple of n. Otherwise, all of the sums are not multiples of n. So the remainders are going to be 1 or 2 or 3 or all the way to n minus 1. So now I have n minus 1 holes and n pigeons, and I could then do the same thing again. But I feel like this is a bit easier. Okay, let's go to the next problem. So let's say that I have chosen 10 numbers from the numbers from 1 to 99. So x is a subset of the numbers from 1 to 99, and its size is 10. Now, I want you to show that there are 2 disjoint non-empty proper subsets of x that have the same sum. Okay, so all of these things are important. I want the sets to be disjoint. So I want to find y and z, and I want these y and z to be subsets of x, but I want them to be disjoint. So I want their intersection to be the empty set. I want them to be non-empty, which means that y is not the empty set and z is not the empty set. And I want them to be proper subsets of x, which means that y should not be all of x and z should not be all of x either. Okay. And then of course I want them to have the same sum. So if I take the sum of all the elements in y, this should be this should be the sum of all the elements in Z. The good news is we don't have any remainder business here. It's just the actual sum. I give you a hint, this is much easier than the previous one. Okay. How many disjoint non-empty proper subsets does X have? So X is a set of size 10. Okay. Oh, sorry, forget about the disjoint part. How many non-empty proper subsets does X have? X is a set of size 10, so it has 2 to the power of 10 subsets. But we have to do -2 because we cannot take X and we cannot take the empty sets. Okay. So we have 1022 non-empty proper subsets of X. Okay. Let's say that this is my set P. My pigeons are going to be all the non-empty proper subsets of X. So I have 1022 pigeons. Okay. And let's say that the function I have just takes the pigeons and maps them to the sum. So it takes, let's say, some element y, and it maps it to the sum of all the elements in y. Okay. So what would my holes be? My holes are all the possible values that this sum can take. Okay. So basically, I'm saying that if I take a non-empty proper subset of X, what are the values that can serve as the sum of elements? So I have this X, I'm taking some non-empty proper subset of it. What is the smallest sum that I can have in that subset? So it's 1, right? Because it's not an empty set, so I cannot get sum 0, but I can get a sum of 1 if it just happens that X includes the number 1, and then I can take 1 itself as a proper subset, right? So I know that this sum, let me copy it. I know that this sum is at least 1. But what is the maximum sum that I can get? Again, look here. X has 10 elements, right? And then I have to take a proper subset of X. So I'm taking 9 elements at most. And if I want to have the largest possible sum, I'm going to take the 9 largest elements here. So 91 to 99. So this sum is at most 91 plus 92, so on to 99. What is this number? Someone calculate it. I'm too lazy to do it. It's 855. Okay. So This means that my holes are going to be 1, 2 to 855. So I have 855 holes. Right. So I have 1022 different proper subsets, and they can have 855 different sums. Right. 1022 is more than 855. So there are two subsets that have the same sum. Okay, so we just proved that there are two subsets, there are two proper subsets. Let's call them A and B. Both of them are, of course, subsets of X, and they're also non-empty, such that the sum of the elements in A is the same as the sum of the elements in B. Okay. Does this solve the problem? No, because I have the non-empty and the proper part, I don't have the disjoint part. Right? So I have found two subsets that have the same sum, but maybe they're not disjoint. Okay, so how do I make them disjoint? Yes, exactly. So I have these two sets. Let's say, again, this is A, this is B. And the sum of the elements in A is the same as the sum of the elements in B. But my problem is that they have some intersection. Let's remove the intersection from both A and B. Right? Then the sum of this part would just be the sum of A minus the sum of the intersection. And the sum of this part will be the sum of B minus the sum of the intersection. So they have to be the same. So basically my set Y would just be A minus B, so this part. And my set Z will just be B minus A, so this part. So this is Y, this is Z. I remove the intersection. Okay, so now Y and Z are disjoint. But do we have the other properties that we wanted? We wanted to make sure that they are also non-empty and proper subsets of X. They are definitely proper subsets of X because A was already a proper subset of X and Y is a subset of A. And the same thing for B and C, right? Are they non-empty? Can Z be empty? What does it mean if Z is empty? If Z is empty, it means that A was the same as B, right? If I don't have any elements here, then I cannot have any elements here either because the sum of Y and the sum of Z are the same. And then that would just mean that A and B are the same. But the way we chose A and B was that they were two different proper subsets. Remember, because I said that I take all of the proper subsets as my pigeons, and then the number of pigeons was more than the number of holes, so I had two different pigeons, right? So A and B cannot be the same, so Y and Z are not empty. So basically, this is how we can find the sets Y and Z. So you see, it's not always completely straightforward. You have to think about, okay, what are my pigeons? What are my holes? And then when I find the solution, how would I change this solution a little bit to get what I want? Okay, let's look at this one. We have 15 people and they have 100 coins in total. Okay, and I want you to prove that two of them have the same number of coins. I don't remember if someone could have 0 coins or not. Consider both cases. So consider this as two problems. Yeah, okay. People can have 0 coins. Any ideas? Okay, look. This is actually not directly applying the pigeonhole principle, but we're going to apply something that is very similar to the simple proof that we had for the pigeonhole principle. So let's just do proof by contradiction. So suppose each person has a different number of coins. Okay, what does this mean? What is the minimum number of coins that I can have? I have 15 people. If they're supposed to have different number of coins, the minimum number of coins that I can have is 0 plus 1 plus 2, so on to 14. Okay, so I will need at least these many coins. Maybe I have more, but I cannot have less than this number of coins, right? Because everyone has a different number of coins. But this sum, if I calculated it correctly, is 105. So if we want each person to have a different number of coins, we will need at least 105 coins. And we have only 100. So two of them are forced to have the same number of coins. Okay, here's another problem where, again, defining the pigeons and the holes gets more interesting. So let's say that we have a football team, and this team has played 20 games. And by the way, we're not in America, so football is the one that is actually played with foot. So we're playing 20 games, and the team has scored in all of them. And let's say that in total, the team has scored 30 goals. Okay. Now, here's the part where things get interesting. Prove that there is a sequence of consecutive games in which this team has scored exactly 9 goals. I just really love the pigeonhole principle because it gives you some of the weirdest theorems. So again, just to make sure the problem is clear for everyone, we have a team. It has played 20 games. In each game, it has scored at least 1 goal. And we know that in total, it has scored 30 goals. Now, what we want to prove is that there was a window, a consecutive sequence of games in which the total number of goals was exactly 9. And by the way, in the exam, if you see any problems like this, if you see problems where they have just a bunch of numbers in them, it's either induction and you have to guess the formula and do induction, or it's pigeonhole. Okay, let's try to give some mathematical names and formalize everything. So the team is going to score some number of goals in the first game. Let's show that with G1. So G1 is the number of goals in the first game. Okay. And then G2 is the number of goals in the second game, and so on until G20. What do we know? We know that all of these GIs are at least 1 because the team has scored in all of the games. And we also know that the sum of the GIs, so G1 plus G2 to G20, is exactly 30. Okay. These are the things that we know. Now, what do we want to prove? We want to prove that there is a sequence and a consecutive sequence. So it means that there is some index I and some index J such that GI plus 1 to GJ sum up to exactly 9. Right. So let's do a simple trick. Let's say that I define AI to be the sum of the first I goals. So like I would say AI is the number of goals that were scored in the first I games. So sum of GJ for J less than or equal to I. Okay. Now, what do I know about the AIs? Again, I know that there are at least 1, but I know that there are also at most 30. Okay. So how many AIs do I have? I have only 20. But how many values can they take? They can take 30 different values. So at this point, it seems like I'm not quite ready to apply the pigeonhole principle yet. Right. But here's the thing. What am I saying? I say that I want to prove there is a sequence of consecutive games in which the team has scored exactly 9 goals. What does that mean? It means that I want to prove that there exist 2 indices, I and J. There exists I and J, such that AJ minus AI is exactly 9. Right? So AJ is the number of goals in the first J games. AI is the number of goals in the first I games. So again, consider my games. If I have a consecutive sequence of games in which I have scored 9, I can just look at game 1 up until the end of here, and I can say this is index J, so I have scored AJ goals here. And then I can say this one is index I, so I have scored AI goals here. So oops, in this consecutive part, I have scored AJ minus AI. And I'm saying that prove that there is a sequence of consecutive games in which the team has scored exactly 9 goals. So this is the same as saying that prove that there is an AJ and AI such that the difference is exactly 9. Okay. And also, in this case, I can even include A0, right? Because I can say my A0 is just 0. So if I look at the first 0 games, I have scored 0. Great. But I still have a problem. Even if I include A0, I have 21 values, right? So I have 21 AIs, A0 to A20, but their values can be between 1 and 30. So still not great. I don't have a good set to use as my pigeon set. Okay, what else do I know? I know that the team has scored in every game. So I know that all the AIs are different. The AIs cannot be the same, right? So I know that all AIs are different. Okay. This is going to give me what I want. Look, I have the numbers from 1 to 30. So let's say I have 1, 2, 3. Oh, this is going to take a while. 5, 6, 7, 8, 9, 10. Kill me now. I really want to die. Okay, so I have these 30 numbers, and I also know that, well, A0 is 0, right? Now I want to choose 20 of these numbers for A1, A2 to A20. And I know that A1 has to be smaller than A2, smaller than A3, and so on. So I have to choose some number as A1, some other number as A2, so on, then A3, A4, all the way to A20. Okay. Now, what the problem says is that no matter how you do this, you will have to choose two AIs, or AI and AJ, whose difference is exactly 9. So let's try to avoid this. Let's try to choose the numbers in a way that the difference of any two numbers is not 9. What does that mean? So let's say that I've chosen, for example, the number 15. Remember, I have to choose 20 numbers. Let's say I choose 15. It means I cannot choose 15 minus 9. So if I choose 15, I cannot choose 6. Okay. I also cannot choose 15 plus 9. So if I choose 15, what is 15 plus 9? I cannot choose 24. Right? So this is giving some intuition. It's like every time that I choose a number to be in my set, there is some other number that I cannot choose. Okay. So let's see. Well, I mean, sometimes there's even more than one number, but sometimes it's just one number. So for example, if I choose 3, then I cannot choose 12. Right? So some numbers have conflicts with only one other number, but some numbers have conflicts with two other numbers. But I can pair my numbers up. I can say, look at 1 and 10. Okay. So if I look at 1 and 10, I can choose at most one of these two. I cannot choose both of them. Right. But I can say the same thing about 2 and 11. Right. And then 3 and 12. Okay. And so on to 9 and 18. So up until now, I've paired up all the numbers from up until here. And then I can say the same thing about the numbers here. So I can say, well, among these numbers from 19 and 28, I can choose only one of them. Right? From 20 and 29, I can choose only one. And from 21 and 30, I can choose only one. Okay, so I've now paired up these numbers, this one, and I've also paired up everything from 28 onwards. Okay, so the only numbers that are not paired are these numbers. So from every pair, I can choose at most one number. And then additionally, I have a bunch of unpaired numbers, and I can choose them maybe as well. Right? How many pairs do I have? Here I have 12 pairs, right? 13, 14, 15, 16, 17, 18. Right. So I have 18 sets. These are my sets. So I'm going to put 22 as its own set, 23 as its own set, so on to 27. I have 18 sets, and from each of these sets, I can choose at most one number. Because if I choose two numbers in the same set, their difference is 9. Right? So I can choose at most 18 numbers so that the difference of any two numbers is not 9, but I'm choosing 20 numbers. So this tells you that this is impossible. This tells you that there is definitely two of these numbers, two of these AIAJs that have a difference of exactly 9. But this was painful. Okay, you all saw me in pain here. So the question is, can we do this in a more elegant way? So instead of just brute forcing it, and what am I saying here? I'm saying that my holes are basically these 18 sets, right? And the pigeons are the elements that I'm taking. the number of elements I'm taking is more than the number of sets, so I'm taking at least 2 from the same set. But if I take 2 from the same set, their difference is 9, right? So, but this was painful. Can I do this in a nicer way? Well, yes. Here's what I can do. I can say, this is the set of pigeons that I want to create. I want to say one pigeon would be A1, another pigeon would be A1 plus 9. One pigeon would be A2, another one would be A2 plus 9. So on, A20 plus 9. Okay. I'm just looking at these 40 numbers, right? I have these 40 numbers, which are basically my A1 to A20, and also the same numbers plus 9. What do I know about the range of these numbers? So I know that each of these numbers is at least 1, but it's at most 39, right? So I have 40 numbers that are between 1 and 39. So 2 of these numbers have to be the same. Okay, does this make sense to everyone? I have 40 numbers, the numbers are between 1 and 39, 2 of them have to be the same. Okay, so I know that 2 of them are the same. But the 2 that are the same cannot both be from the left side, because I cannot have AI equal to AJ. This is impossible. Because AI was the number of goals in the first I games, and AJ was the number of goals in the first J games. And we said that every game had at least 1 goal. So AJ and AI, they're different. They're not the same. But for the same reason, I can also say that it's impossible to have AI plus 9 equal to AJ plus 9, because this would also mean that AI was equal to AJ. So if I have 2 numbers among these 40 numbers that are the same, one of them has to be from the left side, and one of them has to be from the right side. So I should have something like this. Something from the left side, some AJ, is equal to something from the right side, some AI plus 9, which is exactly what I wanted to do. So this means that from game I plus 1 to game J, I have scored exactly 9 goals. Right? Remember, this is exactly what we wanted. We wanted to say AJ minus AI is 9, and this is exactly the same. AJ minus AI is 9. Okay, so you can do the painful way, or you can do this way. Great. Let's look at another. So our friend X is now a subset of the numbers from 1 to 100, and its size is 16. So basically, we have chosen 16 numbers from 1 to 100. Prove that there exist 4 different numbers, A, B, C, D, among the 16 numbers, such that the sum of the first 2 is equal to the sum of the last 2. And again, the important thing here is that we want different numbers. Because of course, if I allowed you to repeat the same number, you have A plus A equals A plus A. Right. Okay, in this case, we need to do a little bit of manipulation. So first of all, what does it mean when I say A plus B is C plus D? I can just move things around, and I can make it something like this. A minus C is D minus B. Okay. So now, instead of sums, I'm talking about differences. So basically, the problem is equivalent to saying, hey, find 4 numbers such that the difference of the first pair is equal to the difference of the second pair. Now, why do I like to do this? Intuitively, because the sums can have very huge values, but the differences can have a more limited set of values. So if I want to create my holes based on the differences, I will probably have fewer holes. Okay, so that's the first simplification. So I want to just say that there are 4 different numbers such that the difference of the first 2 is equal to the difference of the last 2. Okay, so here's the thing. I have 16 numbers. So X is 16. the size of X. So how many different differences between pairs of numbers can I have? I can have 16.2 pairs of numbers. Sorry, 16 choose 2. So what is 16 choose 2? I'm really bad at calculating stuff. 120. Okay. So I trust you on this. So I have 120 pairs of numbers. If I take a pair of numbers, let's say I take A1 and A2, and I look at their difference. What is this range? And let's say that I always pick A1 to be bigger than A2, so I want to always keep it positive. So it's at least 1, but what is this number at most? 100 minus 1, which is 99. Okay. So my differences will range from 1 to 99. But I have 120 pairs of numbers. So if I look at the 120 differences between these pairs of numbers, there are 2 of them that are the same, at least, because I have 120 differences and all of them are between 1 and 99. Okay, so what does this tell you? So there are 2 pairs. Let's call them whatever, A1, A2, and A3, A4. And remember, I always put the biggest number first, such that A1 is bigger than A2, and A3 is bigger than A4. And I also have that A1 minus A2 is equal to A3 minus A4. Okay, great. Does this solve the problem? Are we done? Oh, that's always the trick question. Whenever I ask you, are we done? We're not done. So if we go back here, we said that we want to prove that there exist 4 different numbers, right? But what did I prove here? I proved that there are 2 different pairs, A1, A2, and A3, A4, such that the differences are the same. A1 minus A2 is equal to A3 minus A4. But this doesn't mean that A1 and A3 are different, or A2 and A3 are different. Okay? Can A1 and A3 be the same? No, because if A1 is the same as A3, then A2 is the same as A4, and the 2 pairs are not different, they're the same pair. But I can be unlucky and A2 can be equal to A3. Okay, just imagine something like this. So I have A1 minus A2, so take the number line, I have A1 somewhere, and then I have A2 somewhere. And this difference is equal to the difference between A3 and A4. Let's say I have A3 somewhere and I have A4 somewhere. But maybe the picture is like this. Maybe I have A1 and then I have A2, which is the same as A3. And then this difference is equal to this difference to A4. Okay. So this is a problem. What should we do here? So you see, we found a solution, but the problem is that sometimes we find bad solutions. Sometimes we find solutions where the 4 numbers are not different. So I want to get rid of these solutions. I want to get rid of the solutions where the 4 numbers are not different. But these solutions only happen when I have something like this, when I have a number which is literally in the middle of 2 other numbers. So A2 or A3 here is the average of A4 and A1. Okay. So here's what I can do. I say, let's look at all the numbers that are averages of 2 other numbers, right? And let's kick out the corresponding pairs. I'm just going to remove some of the pairs. I have 120 pairs, and the sums were between 1 and 99. So I can afford to kick out some of my pigeons, right? Because I have way too many pigeons. So I just want to kick out some of my pigeons, keeping the number of pigeons still more than the number of holes. So at least 100 pigeons should be kept. But I want to make sure that I keep pigeons such that something like this cannot happen. Okay, so let's say I have some number A, and this number A happens to be the average of two other numbers in my set. So it happens to be the average of B and C. Okay. So what should I do? Again, from the 120 pairs that I have here, I want to kick out some of them. So if I just kick out the pair AC, or if I just kick out the pair BA, I would be happy. I'm sure that this case never happens with this particular value of A. Okay. But this is not enough. What happens if A is not only the average of B and C, but it's also the average of two other numbers? So the average of, let's say, B prime and C prime is also A. Now, well, in this case, I already have my answer. So if A is the average of B and C, and A is also the average of B prime and C prime, and all of these numbers are in my set, then this difference is the same as this difference, right? So I already found my four numbers. Okay, so now I'm doing a case for it, basically. So I'm saying, let's look at every number and let's see if it can be the average of two other numbers. And if it can be the average of other numbers in two different ways, then I've already found a solution. The problem is over, right? Otherwise, this number A is either not the average of any other numbers, or there's exactly one way of writing A as the average of two other numbers. And when that's the case, let's say I remove the pair AC from these pairs. Okay, so how many pairs am I removing? For every number, I'm removing one pair from my pigeons. I have 16 numbers, so I'm removing at most 16 pigeons. So my number of pigeons, or number of remaining pairs, or I write P's, this can be pairs or pigeons, is at least 120 minus 16, which is 104. Okay. So I did this surgery. Basically, I started with 120 pairs of numbers, and I said, okay, some of them create problems for me, so I'm going to remove the problematic ones. But I showed that I can remove at most 16 of them. So I have 104 pairs remaining, and now this thing goes through. I can find two pairs that have the same difference, and I can be sure that A2 and A3 are not the same here because I've already removed those possibilities. So now finally I have the complete solution. Okay. I'm going to give this one to you as a homework. Let's go to this one. This one was from the last weekly problem set. There are 6 candidates for president. Every pair of candidates are either friends or enemies. And also in this course, whenever we talk about friends, enemies, handshakes, so on, it's mutual. If one person is a friend to someone else, that person is also a friend to the first person. Prove that there are 3 candidates that are all friends to each other, or 3 candidates that are all enemies to each other. Okay. So basically the idea is this. I have 6 people, or let's say 5, 6. And if they're enemies, I connect them to each other with red lines. And if they're friends, I connect them with blue. Okay. I'm missing some of the lines here, so this is also. Okay. Actually, let me just use this is, okay. Yeah. And between every pair, I either have a red segment or a blue segment. I'm not going to draw all of it again, it's hard, right? So I have 6 candidates, and every 2 candidates either have a red edge between them, which means they're enemies, or they have a blue edge between them, which means they're friends. Now, what we want to prove is that we have a rectangle that has only one color. So for example, here triangle. Here we have a triangle that is completely red. So 3 people that are all enemies to each other, right? Here we have a triangle that is completely blue. So 3 people that are all friends to each other. And the theorem says that you have to prove that one of these 2 types of triangles always exists. Okay. And I mean, in this case, I have both types of triangles, but you can imagine if everyone is an enemy of everyone else, then you don't have a friendship triangle. Right? So it is possible that we have only one of these types, but we want to prove that at least one of these triangles exists. So I either have a blue triangle or a red triangle or both. How would you prove something like this? So here's how I would do it. I would say, take one of the candidates, for example, candidate number 1. Okay. There are 5 segments coming out of this point, right? Each of these segments are going to be either red or blue. By pigeonhole principle, 3 of these segments are the same color, at least. Maybe more than 3 of them are the same color, but we have 2 colors and we have 5 segments coming out. So at least 3 of them are the same color. Let's call that color 1. So let's say this is color 1, this one is color 1, this one is also color 1. I don't know anything about the color of this segment and this segment. They might be 1, they might be 2, I don't know. I just know that there is one color that appears at least 3 times, and I'm calling that color 1. Okay. So now I say, look at the endpoints of these segments. So these are the 3 other candidates that have relation 1 with candidate 1. Okay. Now, between any 2 of these 3, there is also a segment. So actually, let me make this one longer so that I can do it like this. So there is a segment here, a segment here, and a segment here. Right. If any of these segments is also color 1, then I have a triangle. I have a triangle with person number 1 and this one, right? And similarly, if, for example, this one is color 1, I have this triangle. If this one is color 1, I have this triangle. So the only case I don't get a triangle is if all of these segments are color 2, but then I get a triangle of color 2. Okay. So in any case, I have a triangle that has the same color on all 3 of its edges. Now, this problem is from IMO at the time of dinosaurs. So 17 people correspond by mail with one another, each one with all the rest. In their letters, only 3 different topics are discussed. Each pair of correspondents deal with only one of these topics. Prove that there are at least 3 people who write to each other about the same. So this is an extension of the previous problem. It's like we have 17 people now instead of 6 people. And then if you look at the color of the edges, we said here that we have 2 colors. We have blue and red. But in this case, they're saying that we have 3 different colors. So we have 17 people. Between every pair of people, there is an edge. But this edge has one of 3 different possible colors. And you should prove that there are at least 3 people who write to each other about the same topic. So again, you want to prove that there is a triangle with the same color on all of its edges. Okay. Here's how I would do this. I'll try to do it exactly like the previous one. So let's look at person number 1. They're writing to 16 other people, right? So 16 edges are coming out. I'm not going to draw all the 16. But these 16 edges can have 3 colors. So there is at least one color that is used in at least 6 of the edges, right? Because 16 is more than 5 times 3. So I have 3 colors. If every color was used at most 5 times, I could have at most 16 usages. But I could have at most 15 usages, but I have 16. So there should be a color that is used 6 times. Okay. So let's call that color 1. So I have this person number 1, and there are I'm going to show this color one with red, let's say. There are 6 other people where the edge to them is red. And then, of course, I have a bunch of other edges. I don't know the colors of the other edges. I don't care. I only care about these 6. Now, again, just as before, I say, look at the edges between these 6 people. So there are a lot of edges between these 6 people. If any of them is red, I have a red triangle because this person had a red edge to every one of these 6 people. So if any of them is red, if any of these edges between pairs of people in these 6 are red, I have my solution. So the only case that remains that I have to solve is if the color red does not appear here at all. So I have 6 people now, and I have only 2 colors between them. This is the previous problem. If I have 6 people and 2 colors, I have a triangle of the same color. So in any case, I have a triangle of the same color. Okay. An interesting problem would be, suppose that I want to say I have 4 different colors and I want to prove that I have a triangle of the same color, then what should I put instead of 17? Okay. And finally, this is a homework problem. Solve this on your own. So I say, let's say we have a sequence A of numbers. So I have a sequence of n numbers, and then I apply a permutation. And then I compute this. I compute A1 minus the first element of the permutation times the second element minus the second element of the permutation, so on, to the last element minus the last element of the permutation. And then I ask, would this product always be even? So basically tell me for which values of n this product will always be even, and for which values of n can this product be odd.